Hey, welcome! Today we're diving into the world of polynomials. But forget boring homework problems. I want you to think of them more like mathematical puzzles, where each one is holding a secret code. And in this explainer, we're going to learn how to crack it.
So you've got these expressions, right? Full of variables and exponents, and they can seem kind of abstract. But the real question is, what are they actually trying to tell us? What secrets does a polynomial really hide? Well, the answer, the key to the whole puzzle, lies in finding something called its zeros. And trust me, this one concept unlocks absolutely everything about how a polynomial behaves.
Now, zeros aren't just some random numbers you solve for. No way. They tell the fundamental story of the function. They show us the most critical points in the polynomial's life, and figuring them out is our first mission. When we talk about a polynomial's key characteristics, we're really talking about these points, the exact spots where its graph crosses the x-axis. Finding the zeros literally tells us where the function equals 0. These are its roots, its solutions. They're the foundation for understanding its entire shape.
So, how in the world do we find these all-important zeros? Well, lucky for us, mathematicians have built up a whole toolkit of really clever methods just for this. It's all about taking a big, complicated polynomial and breaking it down into its essential parts.
We've got a few heavy hitters in our toolbox, like polynomial long division and synthetic division. And yeah, those are powerful methods, but honestly, the most direct and, if you ask me, the most elegant approach is very often good old-fashioned factoring.
And that's exactly what we're going to focus on today. We're going to master one specific, and believe me, incredibly useful factoring technique called chunking. It's a fantastic way to simplify polynomials that look really tricky at first glance.
All right, welcome to the masterclass. We're not just going to talk about this method in the abstract. We're going to roll up our sleeves and walk through a problem step by step. By the end of this, you'll see just how powerful this technique really is.
So here's our puzzle for today. 9x squared plus 21x plus 10. Okay, right away, that 9 in front of the x squared, that's a pain, right? It can make things pretty complicated. But this is exactly where chunking comes in to save the day.
Let's break this down. First, we're just going to rewrite the expression. Notice how 9x squared is really just 3x squared, and 21x is just 7 times 3x? See? There's a common chunk here, the term 3x. Step 2 is the magic move. We're going to substitute that chunk with a simple variable. Let's call it z. And just like that, our tricky problem becomes this super easy quadratic. Z squared plus 7z plus 10. We all know how to factor that, right? It's just z plus 5 times z plus 2. For the final step, we just swap it back. Replace z with our original 3x.
And boom, there it is. The factored form of 9x squared plus 21x plus 10 is just 3x plus 5 times 3x plus 2. We cracked it. We took something that looked complex and with one clever substitution made it totally simple.
But wait, let's not forget our original mission. Factoring is the tool, but finding the zeros is the prize. This is where we get the big payoff. This is the aha moment where it all clicks.
Here's how it all connects. To find the zeros, you just take each of those factors we found, set it equal to 0, and solve for x. So, if 3x plus 5 equals 0, then x is negative 5/3. If 3x plus 2 equals 0, then x is negative 2/3. Those are our zeros. Those are the exact points where our polynomial's graph hits the x-axis.
So that's the big takeaway here. Factoring is the bridge. It takes a complex problem about the shape of a curve and turns it into a couple of simple, solvable algebra equations. That's why this skill is such a game changer. It's absolutely fundamental. Okay, now that we've got a handle on chunking, let's zoom out a bit. This whole toolkit of factoring methods, it operates inside a system with some fundamental rules. And one of these rules is really key to understanding the limits of what polynomials can even do.
Of course, there are other patterns to look for, like perfect square trinomials, which have that nice, predictable factored form. Or the grouping method, which is great for polynomials with 4 terms. It's like having different wrenches in your toolkit. Each one is perfect for a specific kind of job.
And this brings us to that fundamental rule I mentioned, a cool concept called closure. A set is closed under an operation if doing that operation always keeps you inside the set. Think about it like this. If you add 2 whole numbers, say 2 and 3, you get 5, which is another whole number. You're still in the whole number club. That's closure. So, What about polynomials?
So get this, if you take any two polynomials and add them, subtract them, or even multiply them, the result is always going to be another polynomial. They live in this nice, neat, self-contained world, but, and this is the kicker, if you divide two polynomials, you might get something else entirely, like an expression with a variable in the denominator. So polynomials are not closed under division.
And that leaves us with a final thought to chew on. We use polynomials to model just about everything in our world, from the ups and downs of the stock market to the flight path of a rocket. So if these fundamental mathematical building blocks aren't closed under division, if that one operation can break the system, what does that really imply? What happens when our models of the world need to divide?